All right, welcome to the Kirkwood School District, 6th grade Science, Sound, and Light Unit. We're going to take a look today at refraction of light through different materials. When we talk about refraction, we're talking about making light bend. When light rays enter a new medium, they change in speed, causing them to bend or change direction. The bending of light as it enters a new medium, from air to water, water to air, or water to glass, any of those new mediums going from one thing to the next causes refraction. A medium is any material that light can travel through. Refraction can cause you to see something that may not actually be there. This thing that you see is called an image. A lot of times you see that when you place a pencil in water, like it is here, the pencil may appear as though if it were magnified or broken. Great video from Bill Nye to check out refraction through different kinds of lenses. We'll see this soon.
This magnifying glass is making my eye look big. Now, why is that?
I don't know.
Please consider the following.
Okay.
When light enters something like air, water, glass, or plastic, it slows down a little. And when it slows down, it changes direction. See how one eye is lower than the other? See? Take a look at this. Here are three straight beams of light. When they go into the piece of plastic straight, they come out straight. But if the plastic is tilted, the beams of light get tilted. See, they change direction so that they come out this side offset. Now, what would happen if the piece of plastic didn't have straight sides, but had a curved side, like a magnifying glass? Well, the light would change direction, right? Because the surface of the plastic is curved, each beam of light enters the piece of plastic at a slightly different angle, and it changes direction a slightly different amount. Look, over here the beams of light come together at a single point. This is called the focal point. Now, what about the magnifying glass? Well, suppose your eye were over here, and light from the room were bouncing off of your eye and going through the piece of plastic this way. Well, then, the small area at this end would be spread out over a large area on this side. Your eye would be magnified. Ha! Thanks for joining me on Consider the Following. Bill Nye the Science Guy.
Great video on refraction. Let's take a look at figure 8. This is straight out of your textbook. The picture there, the figure there is on your left. When light passes from air into water, the light slows down. Light slows down even more when it passes from the water into the glass. When light passes from the glass back into air, it speeds up again. Light travels fastest in air, a little slower in water, and slower still in glass. Notice that the ray that leaves the glass is traveling in the same direction as it was before it entered the water. So what we're talking about there is we're talking about how much the ray of light bends when it enters a new medium. Every object, every different object, has a different what's called index of refraction. The index means a number, how much light bends when it enters that new medium. There's a list of objects there to the right on the page that are all liquids. But you can see that even though they're all liquids, there are some very different properties throughout those various numbers. Each one of those numbers tells you exactly how much light bends when it enters that new medium. Now, refraction can cause you to see things that may not actually be there. Take a look at this video and see what this lady doesn't really understand.
Today is July 6, 2007, about 4:30 p.m. I'm just wondering what the heck is in our water supply, what the heck is in our oxygen supply, of metallic oxide salts that create a rainbow effect in a sprinkler? What is oozing out of our ground that allows this type of effect to happen? Not just around our sun and our moon anymore, everywhere we look. The visible spectrum is rainbows. This cannot be natural.
Well, what she doesn't really understand is that white light is all the colors of the visible spectrum. Red, orange, yellow, green, blue, and violet are all of the colors in the visible spectrum. We refer to those as Roy G. Biv. That's the part of the electromagnetic spectrum that we can actually see. We can separate out that white light into all of its various colors using an object called a prism. A rainbow occurs not because there's something magical in our water supply and oxygen supply, as the lady in the video was wondering, but simply because light enters a new medium. It refracts. It enters that raindrop. That raindrop acts like a prism, causing the white light to separate and display the visible spectrum. Now, recall that when white light enters a prism, each wavelength is refracted by a different amount. The longer the wavelength, the less the wave is bent by a prism. Red, the longest wavelength, is refracted the least. Violet, the shortest wavelength, is refracted the most. This difference in refraction causes white light to spread out into all the colors Roy G. Biv. Now, this lens that we can use instead of a prism can cause us to refract light and see an image. The type of image formed by a lens depends on the shape of the lens and where the object is. We're going to take a look at the first kind of lens called a convex lens. The thicker in the center than it is at the edges creates a convex lens. I always remembered as convex, X is exit, and that's where you go out. So this is one that curves out. As light rays enter the axis and pass through the convex lens, they're bent towards the center of the lens, just like you saw in the Bill Nye video a minute ago. The rays meet at what's called a focal point and continue to travel beyond. Great diagram of that. You see the light ray enters the new medium, light bends, and creates a focal point. Light over here enters a new medium, bends, and creates a focal point. An object's position relative to the focal point determines whether a convex lens forms a real or a virtual image. Okay, here's a great example of this. A real image is formed if the object is farther from the lens than the focal point. A real image is formed. So here's the focal point. The image would appear upside down. That is a real image. But if it forms a virtual image if the object is closer to the lens than the focal point. So for example, light enters here, but we can't really see that light creates that upside down image. So therefore, a virtual image is formed. And a lot of the times, you don't see a virtual image. A concave lens is thinner in the center, and I always remember it caves in. When light rays hit the axis through the lens, they bend away from the center of the lens and never, ever, ever meet. A concave lens can produce only virtual images because parallel light rays passing through the lens never meet at a focal point. So, what you get here is light rays enter, they bend out from a sort of fake or virtual focal point. So you see these lines are dotted because light rays don't actually do that. Okay? They don't actually bounce back here. Okay? So we see that light rays enter and then they bend out from that center. And then we would seek to find a dot somewhere back here, okay, that would be roughly where a virtual focal point would be. Our goal today was to compare the refraction of light through different materials. Today we looked at different mediums where we could speed up light and slow down light. We also talked about lenses and what happens when light enters a new medium and changes direction because it speeds up and it slows down. Either in a convex lens, it bends towards the center to a focal point, or in a concave lens, it bends away from the center to a virtual focal point.